closed spaces, the IMO define a competent person as a person with sufficient theoretical knowledge and practical experience to make an informed assessment of the likelihood of a dangerous atmosphere being present or subsequently arising in the space. The competent person should be able to carry out a preliminary risk assessment. In the case of a proposed entry into an enclosed space, this will primarily focus on the atmosphere within the space, but will also include a number of related factors, all of which the competent person must properly evaluate. The IMO also say that competent and responsible persons should be trained in enclosed space hazard recognition, evaluation, measurement, control, and elimination. The competent person should have both theoretical knowledge and practical understanding of the hazards that might be encountered, in order to be able to assess their likelihood and potential impact, and to define the precautions that will be necessary. With regard to enclosed spaces, the IMO define a responsible person as a person authorized to permit entry into an enclosed space, and having sufficient knowledge of the procedures to be established and complied with on board in order to ensure that the space is safe for entry. The responsible person may be the same individual as the competent person, or may be another person specifically appointed to the task. The competent person and the responsible person will usually be drawn from ship's personnel, but may, under certain circumstances, be appointed from shore. Superintendents, safety inspectors, dockyard managers, and repair specialists may all assume such duties, and in these cases it is essential that all personnel involved are aware of the identity of the responsible person in particular. It is for the responsible person to decide the procedures to be followed before and during entry into an enclosed space. He will use the findings of the risk assessment to help him in his decisions and planning. The exact procedures will depend on whether the assessment shows there is minimal risk to the life or health of a person entering the space then or at any time in the future. There is no immediate risk to health and life, but a risk could arise during the course of work in the space. Or, the risk to life or health is significant or immediate. Click on the risk situation for more information. Where the assessment shows that there is minimal risk to the life or health of a person entering the space, then routine safety and documentation procedures will be followed. Where the assessment shows that there is no immediate risk to health or life, but that a risk could arise during the course of the work in the space, further procedures and certain additional precautions that will continue to monitor and safeguard personnel will be put into effect. The competent person and the responsible person. It is for small vessels or those with small crew complements may not have the resources to designate either the competent person or the responsible person. In such cases, these positions will normally be filled from shore. In these circumstances, no entry into a potentially dangerous space should be made until a suitably qualified person is available to fill each role. The 12,573 gross registered tons U.S. flag tanker William T. Steele was preparing to load a cargo of benzene at Guayanilla, Puerto Rico. Unfortunately, due to a planning oversight in the manifold rigging, the cargo was inadvertently loaded into the wrong tank, number 9 center, which had been reserved for a cargo of xylene. There was no chance of working with the wrong stowage, so the benzene was transferred out, and number 9 centre was washed and ventilated. 2 crewmen entered the forward end of number 9 centre to insert an isolation blank in a flange in a pipeline, and the chief officer went to the after part of the tank to eject water from the sump area. The 2 crewmen working forward were unaware of the presence of the chief officer. When the flanges in the line were cracked, benzene began to leak out, and the fumes forced the 2 crewmen to leave the compartment without completing their task. Once on deck, one of the crewmen looked back down into the tank and saw the chief officer lying in the bottom. The alarm was raised, and the second officer and several other crewmen entered the space without breathing apparatus to rescue the chief officer. By this time, the master had arrived on deck, and he donned a breathing apparatus and followed the others into the tank. When he reached the second officer some way down into the tank, he noticed that he was experiencing difficulty in breathing and attempted to share his air supply. As he tried to pass the mask over, both men fell the remaining distance to the bottom of the tank. Seeing this, the other crewmen immediately exited the tank. They survived, but all 3 officers died. The subsequent investigation by the U.S. National Transportation Safety Board concluded that both the chief officer and second officer died from prolonged exposure to the highly concentrated benzene vapors, and the master died from the same cause, but also possibly due to injuries sustained in the fall. Is a part of the risk assessment that must take place prior to any potentially hazardous task on board. The risk assessment should seek to establish the hazards that are or will be present at the work location, and then identify the significant risks arising out of the activity. For each potential danger, the competent person must assess the likelihood of its occurrence and the severity of harm should it occur. Those at risk should be identified, as should the way in which they are at risk. A calculated judgment of whether the risk is tolerable is required. Consideration should be given to the effectiveness of existing controls and whether they need modifying or supplementing. The principal hazard associated with an enclosed space, as we have already established, is the atmosphere inside. We will first examine various elements that may be present within that atmosphere and the specific hazards they present to anyone entering the space. Then look at additional hazards that may have a significant bearing on the task to be carried out. If an empty tank or other enclosed space has been closed and unventilated for some time, the internal atmosphere may have become unsafe, because it then contains insufficient oxygen, or has become contaminated, or both. This may be due to a number of reasons, including corrosion, that is, rusting or other oxidizing processes that deplete the oxygen content of the atmosphere may have occurred, particularly if small amounts of water have been left lying in the space. Oxygen-absorbing chemicals may have been present. Oxygen-absorbing cargoes may have been carried. Gases from volatile cargoes may have displaced the oxygen in the tank. Stored items, which are unsealed or have leaked, may have contaminated the atmosphere. Hydrogen may have been produced in a cathodically protected cargo tank used for ballast. Oxygen may have been displaced by the use of carbon dioxide or other fire-extinguishing agent. Inert gas may have been introduced into the space. Crude oil carriers, product tankers and oboes all carry oil as cargo. All power-driven vessels have oil in their fuel tanks. The possibility of exposure to hydrocarbon vapours therefore exists on all ships. Click on the labels for more information. It is not just oil, however, that presents a toxicity risk. Other vessels may be similarly exposed, due to the nature of their trade. Click on the labels for more information. Flammable vapours may still be present in cargo or other tanks that have contained oil products or chemical or gas cargoes. Pump rooms and cofferdams, duct keels and other void spaces adjacent to cargo, fuel and slop tanks may also contain flammable vapours in the event of leakage between the compartments or from equipment in those spaces. Vapours are not the only source of danger to personnel entering an enclosed space. Residues from previous cargoes can be hazardous on contact with the skin or eyes, or may affect the condition of the tank by, for example, making the decks and ladders slippery. Click on the labels for more information. In summary, the risk assessment for entry into an enclosed space should include evaluation of the following potential or existing hazards. The possibility of a dangerous atmosphere being present or arising subsequently in the space, the present and previous contents of the space, the condition of the space, the means of access into the space, the nature of the proposed task in the space, the contents or condition of adjacent or connected spaces, restrictions on free movement resulting from the size and structure of the space, the work location and nature increasing the possibility of heat exhaustion, the effect of poor illumination, any limitations on communications, the impact of weather, sea state, etc. on the operation, constraints on and resulting from any other operations going on at the time, and any other relevant influences and factors. This incident occurred on a tweened-deck dry cargo vessel which was fitted with several deep tanks designed for the carriage of vegetable oil cargoes. She was on a return run to Europe, having called at various small island ports in the South Pacific where she had loaded palm oil in several of the deep tanks. Access trunks led from the main deck on each side between number 1 and number 2 hatches to lobbies at tween-deck level. In each lobby, there was a bolted manhole cover at the top of the appropriate deep tank. The deep tanks were protectively coated and fitted with stainless steel heating coils to maintain the cargo temperature during the voyage and to raise it prior to discharge. The palm oil was discharged in Hull, England, and the tanks were subsequently ballasted with seawater for the next passage to the South Pacific. No cleaning was done after the discharge of the palm oil, and the ballast was loaded directly on top of the remaining palm oil residue. Some 10 to 12 days into the voyage, a crewman was taking routine tank soundings when he noticed a bad smell emanating from the sounding pipes for number 2 and number 3 deep tanks. This was not unusual and regarded as a normal feature of the carriage of ballast water in these tanks, but he did report the matter to the chief officer. Following company requirements, the ballast water was changed after passing through the Panama Canal. Deballasting commenced during the afternoon of the 2nd of October. During the evening watch the same day, the 2 engineer cadets were sent forward by the second engineer to check on the water levels in number 2 and number 3 tanks, as the ballast pump had lost suction. The cadets first checked number 2 tank by going down the access trunk to the tween-deck level and opening a steel screw-down inspection port in the manhole lid. Having established that the ballast seemed to be out, they re-emerged and opened the door of the access trunk to number 3 tank and the pump room. Here they found a foul smell of such strength that they decided it was unsafe to enter, and reported back to the second engineer. On the assumption that all the ballast water was out, both tanks were reballasted with clean seawater. After reballasting, however, the smell from the air pipes of both tanks did not improve. A fleet circular from the company drew attention to the possible dangers of hydrogen sulfide gas evolving from decomposing palm oil in ballast water, and requesting masters to ensure that ballast water is changed at sea, and that under no circumstances was access to the tanks or pump rooms to be allowed until entry procedures had been followed and an entry permit issued. The circular had reportedly been discussed on board at a recent safety meeting, but this had not been minuted. A number of tanks were emptied and cleaned as the passage progressed. On the morning of the 21st of October, the chief officer asked the second engineer to pump the ballast out of number 2 and number 3 tanks. 2 seamen were instructed to remove the lids from the tanks in the 'tween deck lobbies. At about 0700 hours, the Bangladeshi deck serang reported to the bridge to discuss the work for that day. The chief officer anticipated that the 2 tanks would be empty by early afternoon, and discussed preparations for tank cleaning with the serang. There was evidently some confusion, however, and it is possible that the deck serang had misunderstood when the tanks would actually be empty. When they turned to at 0800 hours, the deck serang went forward with 5 men to the tank access trunks. They rigged a hose and prepared a cargo cluster light. The deck serang and 1 seaman went down the access trunk at the starboard side, leading to the 'tween deck lobby, where the manhole access to number 3 deep tank had been opened earlier. The deck serang entered the tank. Almost immediately, the seaman at the manhole shouted up the access trunk, "Serang fall down!" He then entered the tank himself, and the other men on deck heard him calling, "Serang, serang," from inside the tank. Then it went quiet. At around 0850 hours, the third officer on watch on the bridge heard shouting on the deck. At the same time, another seaman alerted the chief officer, and he ran forward. He issued instructions for self-contained breathing apparatus to be brought from the safety locker. Without waiting for it to arrive, however, he also entered the trunk. He was wearing a boiler suit, but no self-contained breathing apparatus, and had not stopped to put boots on. A seaman also went in, but only got a little way and came back out on deck due to the strong smell of gas. A few moments later, the master arrived, closely followed by a seaman bringing a self-contained breathing apparatus. The master donned the breathing apparatus and descended to the 'tween deck level, where he found the hose and cargo cluster which had been rigged earlier. He saw the chief officer slumped on a stringer plate below the manhole, but could not see the others. He considered that he was unable to assist on his own, and returned to the deck. The chief engineer and second engineer had now arrived on the scene, and also donned self-contained breathing apparatus sets. They entered and descended with an emergency oxygen supply. They located the chief officer and started to administer the oxygen. As the chief engineer lifted the chief officer to a more upright position, he noticed another man hanging upside down from the stringer plate with one leg caught in the ladder, later identified as the serang. A stretcher was lowered, but put aside by the 2 engineers as being ineffective in the circumstances. Shortly after this, a self-contained breathing apparatus low-level alarm sounded, but the 2 engineers were unable to identify which set it was coming from. They decided it was safest for both of them to exit, and by the time they reached the deck, both alarms were sounding. Spare bottles had been organised by the master, and the chief engineer, this time accompanied by the second officer, returned inside wearing fresh sets. The second engineer went to get still more cylinders. The chief engineer took a line with him that was rigged through a block at the top of the access trunk. He attached it to the chief officer, and an attempt was made by those on deck to lift him out. The line, intended for lowering tools, was not strong enough, and parted, the chief officer falling back down and landing on a stringer plate. The chief engineer secured the line a second time, but then had to exit the space due to a low-level alarm sounding on his second set of bottles. A third fresh supply was provided, and the chief engineer again returned to the bottom of the trunk. This time he took a lifeline with him and secured that as well. The chief officer was eventually lifted out onto deck at around 1000 hours. Resuscitation and cardiac massage were attempted by the master and purser, but were abandoned when it became apparent that there was no sign of life. As there was no chance of the deck sarong or the seamen inside the tank being alive, the master decided not to risk further personnel, and ordered that deballasting should continue with a view to recovering the other bodies when the tank was empty. The mixture of palm oil residues and salt water had led to the generation of hydrogen sulfide gas and corresponding oxygen depletion within the deep tank and in the vicinity of the tween-deck lobby after removal of the manhole lid, which claimed the lives of the chief officer, the deck serang, and the seamen. The Hong Kong-registered bulk carrier, Nego Kim, arrived off the port of Dampier in the early hours of Saturday the 17th of November 2001 and anchored to await berthing instructions. She remained at anchor over the weekend, during which time the crew continued scheduled maintenance work, including the preparation of the interior of No. 1 port topside ballast tank for painting. At about 1300 hours on Sunday, the chief officer tested the atmosphere inside the tank for oxygen content, in accordance with standard enclosed space entry procedures. At about 1430 hours, the 8-man deck crew started work painting the steelwork inside the tank. One man was using an airless spray painting gun, while the other crewmen maintained the paint reservoir, tended a cargo light lowered through the after manhole, and generally assisted the painter as required. Ventilation of the tank was achieved by an open-ended compressed air hose led from the forecastle, along the deck, and down through this after manhole, and an electrically driven fan, positioned at an angle over the after manhole, which also provided access for the paint hose, light cable, and a lanyard. The chief officer supervised the initial stages of the task. The paint used was a 2-part epoxy mix, thinned as needed using the thinner product supplied by the paint manufacturer. According to the chief officer, the volume of thinner used was between 30% and 50% of the total mixture. At about 1530 hours, the chief officer went to the bridge to start his anchor watch, leaving the boatswain and deck fitter in charge at the tank. At about 1640 hours, a large explosion ripped through the tank. 3 men were blown down the length of the main deck, killing them all instantly. 4 others were blown over the side. 1 man, who had been inside the tank, was still alive but severely burned. He was assisted out of the tank through the ruptured main deck plating and airlifted ashore, but later died from his injuries. A search and rescue operation recovered the body of 1 seaman, but the others were never found. The investigation concluded that the air-vapor ratio, in particular stemming from the paint thinner, had developed into an explosive atmosphere, and that it had come into contact with a source of ignition. It was unable to positively identify that source, other than to say it was within the compartment. The electrical lighting, a VHF radio, or a spark carried down from the electric fan could all have been possibilities, as could a falling tool or a cigarette lighter. It was noted that the prevailing good weather conditions would have increased the temperature inside the tank to around 38 degrees Celsius, which was above the ignition temperature of the thinners, although below the auto-ignition temperature. Analysis of the rate of delivery of fresh air revealed that it was insufficient to prevent the atmosphere entering the flammable range, and that, not being fitted with a trunking to carry the air to the lower part of the space, only the upper region of the tank was being ventilated. We've already seen the potential hazards presented by the atmosphere within an enclosed space. We now need to look at test equipment, test procedures, and required readings in more detail. The readings quoted in this section for safe, unprotected entry into a space are generic minimum readings taken from standard industry regulations and guidelines. If the vessel operates to a safety management system which requires higher or more specific standards, then these should be observed and followed. There are many models of atmosphere test meters available, although most companies try to standardize across their fleets in order to make supply of parts more streamlined and training on the equipment easier. Click on the labels for more information. Testing of the atmosphere in an enclosed space for the purposes of authorizing entry should only be carried out by persons trained in the use of the equipment and listed as approved operators under the safety management system. Testing should be carried out before entry and at regular and frequent intervals thereafter, whilst entry continues. Some monitors have a data logging facility, but in any event, records of periodic tests of the atmosphere in an enclosed space should be made. Such records are filed after use, along with the enclosed space entry permit, for examination by auditors and inspectors. If possible, the testing of the atmosphere before entry should be done by remote means. This may be with a fixed probe in a hold or void space, or with an extension line on a portable monitor. This is the safe way to test, in that it does not expose anyone to the additional hazards presented by entering the space. Vessels where entry into enclosed spaces is routine or anticipated are usually fitted with or supplied with the appropriate equipment. In some vessels, however, entry into an enclosed space may be an exceptional and unanticipated event, and they may not carry equipment with remote measuring capability. In this situation, an initial protected entry must take place to carry out measurement within the space, irrespective of the suspected condition of the atmosphere. The person selected to enter the space to test the atmosphere must wear breathing apparatus and rescue harness, and must position themselves only where they can be pulled out in an emergency. On some vessels, it may be that certain spaces are only accessible by passing through another enclosed space, as for example a double-bottom tank, accessed through a manhole in the bottom of a side ballast tank. In such cases, this must be carefully planned and all precautions accounted for. It may be that the operation becomes a two-phase entry, with separate atmosphere test readings and an intermediate station for a second attendant. If the enclosed space is a cargo tank or hold, it is assumed that cleaning operations are completed and the space has been cleaned to the maximum possible extent, followed by adequate ventilation. The meter used to test the atmosphere should have been purged and zero set immediately before use and allowed to stabilize. Oxygen meters should be zero set in clean, fresh air, not immediately adjacent to the hatch or vent risers, where they may be subject to fumes being expelled from the tank. The ventilation should be stopped about 10 minutes before any tests are made, and not restarted until the tests are complete. This is to allow the atmosphere to settle into an even representative condition. For readings subsequently taken while the space is occupied, ventilation should not be stopped, but run continuously. Testing must be carried out at different levels and in different sections of the space, thus increasing the possibility of detecting any pockets of oxygen-deficient atmosphere remaining in the space. Suspected vapours, which have a relative density greater than that of air, will be found at the bottom of the space. Vapours will also tend to remain where the ventilating airflow is least effective, that is, at greatest distance from the inlet, and particularly between frames and stiffeners. Note that an extension fitted to a portable monitor may require additional steps in the test procedure. Most models today are electronic, but where an air sample is drawn up to an analyzer unit on deck, a longer sampling time may be required to allow fresh air to be purged out of the piping and ensure that an accurate reading is obtained. Note too that some models are not capable of drawing a sample above a certain height and cannot therefore be used to test the atmosphere in the bottom of a tank from deck. When it is required to gas-free a cargo tank on an oil tanker after washing, it should first be purged down with inert gas to reduce the hydrocarbon content to 2% or less by volume, so that during subsequent gas freeing, no part of the tank atmosphere is brought within the flammable range. This additional gas freeing is also needed to remove toxic products introduced with the inert gas. Direct measurement of trace components of inert gas is not required when that subsequent gas freeing reduces the hydrocarbon concentration to 1% of lower flammable limit or less, in conjunction with a steady oxygen reading of at least 20% by volume, because this is sufficient to dilute these components to a safe concentration. On the 4th of September 2001, the chemical tanker Rheinstern was anchored off Rotterdam awaiting cargo orders. Even though there were no instructions, the master decided to prepare the tanks anyway. The previous cargo had been naphtha. Because of the vapour density of the product, the plan was to ventilate the tanks and then eject the cargo residues, collecting them in a slop tank. No water cleaning was planned. Ventilation was achieved by a flexible large-bore trunking connected to the deck ventilation line and inserted through an adjacent tank cleaning hatch. The trunking was only pushed inside the top of the tank and not lowered down to the bottom. The tank lid was kept only cracked open in order to create a slight back pressure in the space. In order to eject the tanks, the normal procedure was for a man to enter the tank and put the ejector pump suction hose into the sump, directly under the foot of the deep well cargo pump. The first tank to be ejected was number 8 starboard, and the chief officer tested the atmosphere at around 10:30 hours, recording 15 to 25% LEL and 20% oxygen content. The chief officer had given instructions that self-contained breathing apparatus was to be used in the tank entry, but he later observed a number of the crew exiting tank number 8 starboard after ejecting wearing filter masks. The chief officer spoke to one of the men who stated that they preferred to use the filter masks because the SCBA sets were heavy and awkward to use. Work continued through the day, and the chief officer later left the deck to get some rest. At around 16:35 hours, the crew turned their attention to tank number 6 port. The tank was not tested before entry, the assumption being made that conditions would be the same as in number 8 starboard. The deck cadet had by now arrived on deck and was assigned as watchman. 3 crewmen went into the tank, 1 to place and tend the suction hose, and 2 to squeegee, or sweep any remaining product towards the sump. At around 16:45 hours, the deck cadet saw one of the men down the tank collapse. He immediately informed the second officer on the bridge, and the general alarm was sounded. The master quickly appeared on the bridge, but, discovering the situation, he went down onto deck straight away. On the way, he met the third officer and instructed him to collect a rescue line and harness from the after-deck store. Meanwhile, one of the two crew members, still standing in tank number 6 port, left the tank to get a breathing apparatus, while the other crew member stayed with the man who had collapsed. As the man arrived on deck, the deck cadet took the filter mask from him, put it on, and entered the tank himself to take a breathing apparatus set down. Once he had handed it over, he returned to the deck. The man who had stayed inside fitted the mask to the casualty and opened the air supply valve, establishing at the same time that he was breathing. The crewman who had left the tank now returned wearing a self-contained breathing apparatus and took over from his shipmate, who had been wearing only a filter mask throughout the incident. As he exited the tank, the master took the filter mask from him, put it on, and entered the tank. He tried to move the collapsed man, but he found him too heavy, gave up the attempt, and climbed back out onto deck. By this time, both equipment and men had started to arrive on scene, including the harness, line, and a resuscitator. 2 more men donned self-contained breathing apparatus and went down inside the tank. The harness was lowered and fitted to the casualty, who was then hauled out onto deck. During this recovery operation, the master collapsed on deck. The second officer contacted the Netherlands Coast Guard from the bridge and requested medical assistance. After some discussion, it was agreed that the Rhinestone should heave anchor and proceed towards the entrance to the port, in order to minimize further delays, and a helicopter would be mobilized. In the meantime, repeated and prolonged attempts were made to revive the master, and care was administered to the man who had been brought out of the tank. At 18:30 hours, the helicopter arrived bringing a doctor. The master was pronounced dead at the scene. The man who had collapsed in the tank spent the night in hospital ashore, but returned to the vessel the following day.